Hello and welcome to this video. So in this video we will finally get the solution or compute the solution of this. We'll finally compute the solution of this. Now remember this function I kept over here on the right? In reality actually we do not need it. It really doesn't help us to have the inverse Laplace transform of 3 over s squared plus 2s plus 7. And having it really doesn't help us much, but yeah, we'll still keep it there and see how our solution compares to this. So first we need to decompose this into partial fractions, or we need to expand this into partial fractions. To expand this into partial fractions, we have a repeated root. So you have k1 over s plus k2 over s squared, because s squared is a repeated root. That's two roots at 0. Then we have this parameter over here. Now the question is this: do you have real distinct roots here? If we have real distinct roots or real repeated roots, then we have to then we need to expand that. Okay, so to determine that, we need to find b squared. You remember, okay, where do I write this so I don't confuse things? Okay, let's have our b squared here. B squared. So b squared in this case will be 2 squared. So that will be 2 squared, which is equal to 4. And then 4ac will be equal to 4 times 1 times 7, because this is a and that is c. So 4 times 1 times 7, and that gives us 28. Okay, so we have 4 and 28. Is b squared less than 28? Yes. So b squared is less than 28. That means that we do not have real roots. The roots are complex or imaginary. Well, complex. So because roots are complex, we cannot break this apart. We have to keep this together. So we have k3s plus k4 divided by s squared plus 2s plus 7. Okay, so let's go ahead and expand or make this a single fraction. In the denominator you'll have s squared into s squared plus 2s plus 7, and in the numerator you'll have k1s into s squared plus 2s plus 7 plus k2 into s squared plus 2s plus 7 plus k3s plus k4 into s squared. Okay, I believe you know how I arrived at that. I mean, I don't think I need to walk through the mathematics of this simple algebra. So based on this, we can now equate the numerators. So that means that 3 is equal to, and what I want to do at this point is not just expand this, but also collect the like terms. So for instance, by the time you expand this, you have k1s cubed. Here you have k3s cubed. So I'll put s cubed. Let's get the s cubed terms together. k1 plus k3. Next, I want to get the s squared terms together. Here we'll have an s squared, 2k1s squared, so 2k1, plus you have an s squared term here, k2s squared, k2, plus you have an s squared term here, k4s squared, plus k4. We are done with these terms. We've used the s cubed term and the s squared term, so just to take note that we are done with this. Here we have used the first term and the second, so we just have this left, plus the s term, and you have 7k1, that's 7k1s, plus you have, so we're done with this term here, and we're left with this one, 2k2s plus 2k2, and then constant terms, we're just left with 7k2. So our 3 is equal to this. Now, like we did earlier on, we're going to simply equate the left and right hand sides. We're going to look at the powers of s. So looking at the in fact, the easiest way to start in this case is just start from the constants, because on the left hand side you do not have any powers of s. So let's just start from the constants. I think it is clear that 7k2 is equal to 3, which implies that k2 is equal to 3 over 7. Good. Now let's walk smart. Here we have two unknowns, k1 and k2, but we just computed k2. So let's look at this term. You have 7k1 plus 2k2 is equal to 0. We already know the value of k2 as 3 over 7. So we have 7k1 is equal to minus 2 into 3 over 7, which gives us minus 6 over 7, and that tells us that our k1 is equal to negative 6 over 49. Okay, so we have k1 3 over 7, k2 3 over 7, k1 minus 6 over 49. Let's come to this side if you don't mind, and let's get the next parameter. So we could do either of them. We could take this s squared term. So let's take the s squared term. We already know k1 and k2, so all we don't know is k4. So we know that 2k1 plus k2 plus k4 is equal to 0. We could take these terms to the other side and substitute in their values. We simply have our k4 being equal to minus 2k1. k1 is this, minus 2 multiplied by that gives me 12 over 49 minus k2. k2 is 3 over 7, so we have minus 3 over 7. So we had minus 2k1 minus 2k2 on the right hand side. Okay, so this is what we have over here. Now let's go ahead and compute this. This is the same thing as 12 over 49 minus 21 over 49. All I did here was multiply this term by 7 over 7. Okay, so that's minus 21 over 49, and that gives us negative 9 over 49. Cool. We're left with one term, the s cubed term. So we have k1 plus k3 is equal to 0. Make k3 the subject of the equation. This implies that k3 is equal to negative k1. We already know k1 is minus 6 over 49, which is equal to 6 over 49. So we have all our terms. Now that tells us that y of s is simply equal to, do we have that term? Can we have it on the screen? Yes, we can have it on the screen. So we have k1, which is minus 6 over 49. So minus 6 over 49 divided by s plus k2. k2, 3 over 7. 3 over 7 divided by s squared plus k3s plus k4. k3s, 6 over 49 s plus k4. k4 is minus 9 over 49, so I'll take this minus 9 over 49. All this divided by s squared plus 2s plus 7. Let me bring this down a little bit. So you have s squared plus 2s plus 7. Okay, so now we have our expression and we want to find the inverse Laplace transform of this. This we can easily work with. Well, maybe not easily, but we can work with this. So we have y of t, that's the inverse Laplace transform, is equal to, I'll start this out, I won't do the full solution of this, okay? So that's minus 6 over 49 u of t plus 3 over 7. This is a ramp, so 3 over 7 t u of t plus this expression over here. Now I will not compute this by hand because we just take a while, and we have already done a similar example in the last video, so that there's no point in me using your time right now to do this computation. However, I will solve it using a tool that you already know how to use because we dealt with it in our second year. Cool. So now we have this expression. Let's find the inverse Laplace transform of this. To find the inverse Laplace transform of this, I'll go into MATLAB and let's go ahead and compute. Now to find Laplace transforms or inverse Laplace transforms, we need to use the Symbolic math toolbox. So the first thing I'll do is define s as a symbolic variable, so I can just simply create I can use it as a parameter. To find the inverse Laplace transform, the command is iLaplace. Okay, so we want to find iLaplace of 6 over 49s plus 9 over 49. So that's, let's have that in the numerator, 6 over, okay, let's say 6 times s over 49 minus 9 over 49. And all of this divided by, I believe it is s squared plus 2 times s plus 7. Sorry, this should be 2 times s plus 2 times s times 7. Let's just confirm that. S squared plus 2s plus 7. Okay, good. So that is s squared plus 2s plus 7. So we tell MATLAB, go ahead, find the inverse Laplace transform of this for me. and here is the inverse Laplace transform. Now, just in case you're finding you're finding it a little difficult to picture what this looks like, there's a command pretty in MATLAB that makes things look better. Now look at this expression, and you see you have 6 over 49 multiplied by the exponential of negative t, cosine of square root of t, and then you have another expression over here that has a sine of the square root of t. So it's still an exponentially decaying sinusoid, really. That's what you have over here. So let's go ahead and copy this. I want to write this out, so I'm trying to just see if I can memorize it somewhat. So this is equal to minus 6 over 49, that doesn't change, u of t, plus 3 over 7 t u of t. And then here you have 6 over 49, I think it was 6 over 49, multiplied by the exponential of negative t, cosine of the square root of 6 multiplied by t. Then I think it was minus, if I remember well, it was 5 times root 6 over something multiplied by 6 over 49. Sine root 6 of t. Let's check what I am missing in this. Okay, so 5 times the square root of t, square root of 6 divided by 12. Okay, 5 times the square root of 6, 5 times square root of 6 divided by 12. Okay, so this gives a 2 here, so we could write this as 5 root 6 over 98. I'm sure there's an easier way to write that, but I won't bother about that just now. So we have minus 6 over 49 u of t, plus 3 over 7 t u of t, plus 6 over 49 e to the power of negative t cosine of root 6t, and minus 5 root 6 over 98, I believe that is 2 times 49, 98 sine root 6 of t. And this is our inverse Laplace transform of our original expression. Finally, we have a solution to this. Now, let's just go ahead and try to compare this latter part, that in other words, the inverse Laplace of this parameter over here. Let's compare that to what we had over initially at this point. Notice you have the root 6 popping up, and you have the sine of root 6, and you have e to the power of negative t. So you see that they have effectively the same frequency of oscillation, but amplitudes are different. Oh, I left out the e to the power of negative t on this side. So sorry about that. E to the power of minus t. No, that is not well written. So I should have an e to the power of negative t over here. Can I squeeze that in here? So I hope you don't mind if I squeeze it in here. Okay, so e to the power of negative t. Okay, yeah, so I'll just keep it at that. I do apologize, I left that out by mistake. So we see that there is some semblance in it, but then we see that we actually did not need to keep this information at all, because 3 over s squared plus 2s plus 7. The point is this 3, the numerator here, 3. The s squared plus 2s plus 7 is what determines, is what causes the e to the power of negative t and the sine of the square root of 6 multiplied by t. But the numerator in this case, when we do the partial fraction expansion, is very different. What we have here is 6 over 49 multiplied by 2s minus 3. Okay, so you still have that 3 over s squared plus 2s plus 7. However, you have something else in the numerator, and so that changes the whole dynamics of the entire system. Now, if you're somewhat curious to just be sure that we actually had the solution, then let's go ahead and say yt2. Let's say we want to find the inverse Laplace transform of the original expression that we had in the first place, which was 3 divided by s raised to power 4, s raised to power 4 plus 2 times s raised to power 3 plus 7, I believe that is. So if we tell it to find this, and again, let's just make it look pretty, sorry, make it look pretty, why do you keep on doing that? Okay, let's say pretty yt2. So this is the expression. We have 3 over 7t, just check that out, 3 over 7t minus 6 over 49 u of t, minus 6 over 49 u of t. Then we have these two terms that we got a little earlier on. That's these two terms here, the sine term and the cosine term. So we see that we actually did not make a mistake in our computation. So that is how to find the inverse Laplace transform. Just in case you are curious, let's as well have the Laplace of, let me say y of s, or let me just call it ys, is equal to Laplace transform of yt2, just in case we are wondering whether we can go backwards. And we have this, let's say again, pretty ys. Okay, no, sorry, let's say pretty simplify. Let's simplify ys so that it combines all of them, if possible, into a single fraction, and it does. We have 3 over s squared into s squared plus 2s plus 7, which is our original expression. So yes, we can actually go back and forth between what we had. So that is where we'll end our discussion on the inverse Laplace transform. And yes, it has been a couple of videos, but I believe you have everything in your arsenal right now to find inverse Laplace transforms and to find Laplace transforms. So in the next video, we'll go ahead and talk about the modeling of systems. We'll probably just start with an electrical system in the next video. See you there.